Welcome and hello. This is a video tutorial in the FHWA hydraulic toolbox, and we're going to be talking about the Riprap calculator, specifically covering piers and abutments. So in the previous lesson, lesson 10, that was more of an introduction to the Riprap calculator with a couple structures discussed. And in this video, we're going to discuss bridge piers and bridge abutments. So these two structures are oftentimes associated with bridges. All right, so what I have on the screen here is the FHWA hydraulic toolbox. I have a project already loaded up, and let's go ahead and create our new riprap analysis. Riprap analysis is right here. I'll just go ahead and double click and bring up the dialog box. And then for the structure type up at the top, what I'm going to be discussing is pier and then abutment slash guide bank, these two structures right here. Let's go ahead and get started, starting with pier. Here is the user's manual and what it says on page 43. This is chapter 11.2, bridge pier. This is the governing equation for the diameter. This is the D50 diameter, I believe. Yeah, D50 rock size fraction in inches. And then it also references this HEC Circular 23 Volume 2 Equation 11.1, which I found is a little bit more helpful because it actually defines these parameters in the equation a little bit better, and it typically provides some figures. So let's go there. This is the HEC number 13 PDF file. I'll go ahead and leave a link to this PDF in the description of this video. Design guideline 11 is riprap at bridge piers. All right, so here's the introduction. And then if I scroll down a few pages right here, this is the same equation we were looking at previously, 11.1. Yep. D50 is the particle size at which 50% is finer by weight. So that's what we're solving for here. And then in the numerator, we have 0.692 times this velocity, design velocity squared, all divided by the specific gravity minus 1 times 2 times g. So you can see all the parameters right down here. S of g is the specific gravity, g is the gravitational acceleration. And then for this design velocity, that is defined a little bit further down here. So we have the average channel velocity multiplied by these two factors, k1 and k2. K1 is the shape factor. It's equal to 1.5 or 1.7 based on the pier shape, whether it's round nosed or square face. And then K2 is a velocity adjustment factor, which is as low as 0.9 if the pier is off to the side of the channel, closer to the bank, and as high as 1.7 for a pier that is more towards the center of the channel and receiving the max velocity of the channel or the river. All right, let's go back to the toolbox now and then start adding the data. For the channel data, we need to either define a channel by creating one right here, click on channel calculator, and then we can specify what does that channel look like. Or what I'm going to do is just use an existing channel, channel 1, which I've already defined right here in the project, channel 1. So let's just go ahead and do that. I'll select channel 1. When I do that, all the channel results pop into place here. So the design flow is 50 CFS. The channel depth is 2.34 feet. You can read all the other parameters right here. And then some of those values have moved down here. So the channel average velocity at the bridge is 2.508, and that is derived from 50 CFS divided by 19.937 area. That's the cross-sectional area. So Q divided by A is my average velocity. Some of the input parameters here I'll talk about now for the pier riprap calculation. For the velocity input type, I'm going to use average velocity at the bridge. Otherwise, if I set it to local velocity at the pier, then we wouldn't have to multiply by that K1, K2 factor. But I want to demonstrate that, so we'll just use average velocity at the bridge because that's what it is anyway. And then here are the two factors. Velocity adjustment factor for the location of the pier itself. 0.9, like I said, is if the pier is off to the side. There's some notes here to also kind of help you out. And if I change it to 1.7, that would be a pier that's more centered in the middle of the river. That's always exposed to the flow of the water. All right, the shape factor, our options are round nose pier, and then the other one is square faced pier. So let's go with round nose pier. That is K1 equals 1.5. Anyway, the design velocity would be 2.508 feet per second times 1.7, and then times another 1.5 because of the round nose pier. All right, the next parameter down here is the pier width, which is normal to the flow. So this is the width that the flowing water is going to collide with as it's going to approach the pier. So let's just go ahead and type a number in. I'll say 5 feet. The contraction scour depth. This is the estimated vertical lowering of the stream bed around the pier that results from the narrowing or contraction of the flow area in the channel. I'm going to be conservative and just say 2 feet. And then the bed form depth, I'll also be conservative and say 1 foot. So the bed form depth is the vertical height of natural bed forms like dunes or ripples that develop on the channel bed under the given flow conditions. Lastly, the specific gravity is 2.65. I'll just go ahead and use that. With all of these numbers provided, we can now scroll down and look at some of our results. So the results start right here. The design velocity is 6.395 feet per second. The D50 size is 81 millimeters. So that comes out to about 3.2 inches. Definitely small, perhaps not even necessary. And that would result in class 1 riprap. So here's the class 1 riprap size. And it says as a suggestion that riprap shape should be angular. Okay. A few other layout parameters down here. Let's go ahead and adjust the velocity. Let's change it from 1.7 to 0.9. So what that will result in is even smaller design velocity and smaller D50 in riprap data. Okay, so if I scroll down here, design velocity is now as low as 3.38 feet per second, and the D50 is now as low as 22 millimeters. That's less than 1 inch. So we're kind of going the wrong direction. Let's change that back to 1.7 for that velocity adjustment factor. And next, what I'm going to do is increase the flow rate, the design flow. So you can do that manually by going up to right here. Oh, hold on. Maybe I just need to change the channel data. Okay, so instead of 50 CFS, I'll say it's 100 CFS. Click calculate, click OK. Okay, so now the design flow is 100 CFS. That would have changed some of our hydraulic properties as well as the design velocity is now up to 7.8 feet per second. The D50 is now 121 millimeters. That's about 4.8 inches. We're still using class 1 riprap, but it looks like the D50 of 120 is approaching the 165 D50 for this particular class of riprap. So that's how the here riprap calculator works. I just wanted to close that discussion out with a revisit to the HEC 23 document, specifically on page 217. I have written down a few other specifications and guidelines that are actually pretty helpful. For instance, it mentions that the proposed gradation criteria are based on a nominal target D50 and a uniform ratio of D85 over 15 that aims to be 2, the target uniformity, and the allowable range there is between 1.5 and 2.5. So anyway, this HEC 23 document has lots of good info. It also has an example problem. If you go down to page 231, which is right here, here's an example application. They give you some example numbers. You calculate the design velocity and then the D50 and actually a few more things after that with some diagrams. So go ahead and check that out if you're interested in designing riprap for bridge pier. Okay, so the second part of this lesson is the abutment and guide bank. Let's go to the user's manual here. Go down to page 44. Here's the bridge abutment or guide banks. Typical cross-section of abutment riprap. And then we have an equation below that. D50 over the depth equals all of this over here to the right side. Again, we don't have the exact parameter definitions in the user's manual. So let's head over to the HEC number 23 document. And now we're headed to page 285. I have my notes. Here is design guideline 14. This is where the conversation begins about riprap at bridge abutments. Then if we go down a page, we see a figure. This is why we need riprap for abutments. Here's an abutment that is severely eroded. Scour of bridge abutment and approach embankment. All right, so let's go down a couple more pages. This is page 285 now, equation 14.1 and 14.2. So you use 14.1 if the Froude number is less than or equal to zero point 0.8, and if the Froude number is greater than 0.8, you use 14.2. Let's just talk about these parameters real quick. So D50, we know what that is. It's the grain size associated with 50% finer by mass. Y, that is the channel depth. Let's see, depth of flow in the contracted bridge opening. K is going to either be 0.89 or 1.02 based on if it is a spill through abutment or a vertical wall abutment. S sub S is specific gravity. Usually that's S sub G, but okay. And then V, average channel velocity at the contracted section. Y again is depth, and then G is the gravitational acceleration. So if we're using the Froude number greater than 0.8, it's all the same parameters down here, except the values for K decrease by quite a bit, 0.61 and 0.69 for the spill through abutment and vertical wall abutments. And also there's this exponent 0.14. That's the only difference that I noticed. All right, so we're back at the calculator here. I'm going to select on abutment slash guide banks. We have a new calculator with new parameters to deal with. The abutment slash guide bank structure type is used to size riprap for protecting bridge abutments and guide banks from local scour and erosion caused by channel flow contraction and turbulence. So up at the top, we have our channel. So we'll just stick with our channel 1 design with all of its parameters. The design flow right here is 100. Let me go ahead and change that back to 50, and then we can change it back to 100 later if we want. Calculate and OK. Okay, it looks like whenever I do a calculation, it likes to resize these columns. And this first column for parameter is absurdly large, so that's why I'm making it smaller, but whatever. Down below that, we have our input parameters. And then, of course, at the bottom is our results. So let's talk about these input parameters. The structure type, I'm going to select abutment. And then our other option here is guide bank, but let's stick with abutment for now. Abutment type is going to be either the spill through abutment or the vertical wall abutment. So whichever we select here, this will affect that K variable that we saw in the equation right here. So spill through abutment and vertical wall abutment, that's the K variable. All right, next down is the setback length. I'm just going to make up a number and say 10 feet. The setback length is the distance from the near edge of the main channel to the toe of the abutment. And then next down is the main channel average flow depth. Oops. Okay, so yeah, it's resizing that first column. Nothing I can do, I don't think. Main channel average flow depth, 2.347. And then flow depth at the toe of the embankment, 2.347. That's coming from the hydraulic data, the channel data. And then there's also this parameter called setback ratio, or SBR, which is going to be the length, your setback length of 10 feet divided by the main channel average velocity of 2.347. So that quotient currently is sitting at about 4.26. It's less than 5. But anyway, that setback ratio is used in this abutment calculator. And when that SBR, that ratio is less than 5, the average velocity in the bridge opening provides a good estimate for the velocity of the abutment. Okay, next up is the overbank discharge. So I'm again just going to kind of make up a number and say it's 10 CFS. The total discharge is 50 CFS right here, so it can't be more than that. And then the total bridge area, 19.9 feet squared. That's the flow area, I believe. Setback area, I'll just go ahead and say 5 feet squared. Maximum channel velocity, 2.5. Oops. Okay. I just clicked off that 2.508 feet per second, and specific gravity of the riprap is 2.65. All right, with all those numbers in here, we can now scroll down and look at some of our results. Here's that setback ratio, SBR, of 4.261. The characteristic velocity is 2.508. Froude number is 0.289, so definitely subcritical, certainly less than 0.8. So we'll be using that first equation, 14.1. The abutment coefficient, 0.89. Here's the D50 number. It's 32 millimeters, so a little more than an inch. Very small. Definitely using class 1 riprap. It says that the riprap should be angular. Okay, let's modify a few things. In fact, let's increase the discharge and then see how that affects the D50 and the riprap class. Also at the bottom here, it looks like there's some layout parameters, so that's cool. Very low flow though, so not very aggressive riprap required in this situation. Until I increase the total discharge, let's make it say 200 CFS. Then if I tab off, it'll recalculate. Let's scroll down, and now we have a D50 of 275 millimeters, and that is requiring a riprap class 3, which has a D50 of 317 millimeters, which is about 12 and a half inches. So much larger riprap for class 3, which is required due to the higher discharge values and much higher characteristic velocity as well. We're up to 10 CFS. Back to that HEC number 23 document, if we scroll down to page 294, this is the beginning of an example problem. You can go ahead and do this problem as well if you're interested in really becoming well familiar with this type of riprap calculation for bridge abutments. Step 1, find the setback ratio. Step 2, determine the characteristic velocity. Step 3, check the setback ratio to make sure you're using the correct velocity. Calculate the Froude number, then calculate the D50 based on the Froude number and the correct equation and all those parameters. Finally, step 6 is your results. So this is a nice to have an example problem like that. All right. The last part of this lesson talks about guide banks, and the user's manual doesn't actually say anything different about bridge abutments and guide banks. It just kind of includes both of these topics in 11.3. However, in the HEC 23 document, there's a whole separate section for guide banks, which starts here, design guideline 15 for guide banks. I'm not going to talk about that though, because I want to focus on the user's manual and the interface for the hydraulic toolbox. One thing I'm sure is if you're designing for guide banks, you would change your structure type right here from abutment to guide banks. Everything else in this interface seems to look the same or similar. All right, well, that's it for this lesson. What we talked about was the riprap calculator in the hydraulic toolbox, specifically dealing with piers and abutments.